All right. In this next part of our discussion, let's start talking about the Routh-Hurwitz Criterion. Okay. So what is the basic idea? The basic idea is to be able to deal with higher order polynomials that we cannot directly solve for all the roots without any computer support. Okay, so we rather would like to be able to get the locations of all roots of Q of S equals 0 with respect to the left half slash right half plane without solving for all the roots. For all roots. And what's going to be that useful for is that if we know how many poles are in the left half plane versus right half plane, we can predict stability of the system. Okay, so the requirement is that Q of S should be with constant real coefficients. Okay, Q of S with in fact with real coefficients. There may be parameters inside. That means the polynomial may be a function of a particular parameter. Okay, so let's take a look at the procedure. Okay, so given the characteristic equation in polynomial form, so we write it from the highest order of S towards the lowest order of S. So it starts with A0 S to the power n plus A1 S to the power n minus 1 plus A2 S to the power n minus 2 plus an equals to 0. So we write down our polynomial. Okay. Now, in order to have all roots, for all roots to have real parts of them on the left half plane, the first thing is the necessary but not sufficient set of conditions. Necessary but not sufficient conditions are that we should have all coefficients having the same sign. Same sign, and also none of the coefficients should vanish. None of the coefficients except maybe the first and the last, except A0 and AN should vanish. Okay, so what does that mean? That means that if any one of the coefficients have a different sign, that means we cannot have a stable system. That means we don't have real parts of all the roots smaller than 0. Okay, so that's a necessary condition. We should have all coefficients with the same sign. Also, if we have a missing coefficient, except a0 and an, which can be 0, and I'm going to talk about it in a minute. If we have any missing coefficients with any one of the other powers of S, that means you automatically have an unstable system. Okay. Now, what happens if a0 or an vanishes? Now, if a0 vanishes, take a look. What happens is that Sn goes away and you have a polynomial with one less order. So it doesn't matter. Your system is not of nth order, but n minus first order. So that's not a big deal. What happens if an vanishes? In that case, the smallest power of S becomes S to the power 1. And therefore, you can take everything into S parentheses. And that means it's going to be S times another polynomial with 1 degree less. So that means in case B, you have one of the poles being equal to 0. Okay? So these are the necessary conditions. If any one of these two conditions are violated, we have an unstable system. Now, if both of them are satisfied, that doesn't mean that we have a stable system. That's why we call it not sufficient. Okay? So if these conditions are all satisfied, we need to proceed with the third item, in which case we will construct the Routh array. Okay? Construct the Routh array. This is basically a procedure. Okay? So what we will do is we will arrange the coefficients of Q of S in two rows, and proceed with the Routh procedure. Now, Routh procedure is a table-based calculation. Okay, so let me take it into quote unquote. It's a calculation based on a grid of numbers. Okay, so we will construct the Routh array, and let me show you how we can do that. So we will start with s to the power n, s to the power n minus 1, s to the power n minus 2, s to the power n minus 3, up to s1 and s0. This is known as the indicator column. Okay, so the first two rows are constructed from the polynomial. So we will use our coefficients. Okay, if we consider the coefficients here, starting from a0 to an. So here in this first two rows, we will put the coefficients as such: a0 here, a1 over here, a2, a3, a4, a5, and you continue like this until you exhaust the entire polynomial. So what we do is we have coefficients here that we need to calculate. Okay, so we will have b1 here, b2 here, b3 here. And what we will do is, in order to calculate b1, okay, we will basically have a multiplication over here. So b1 will be given by a1, a2 minus a0, a3. Okay, a0, a3 divided by a1, the coefficient over here. Okay. Similarly, B2 will be calculated as, this time we will do it like this. We will have A1, A4 minus A0, A5. So like this, A0, A5 divided by A1 again. Okay, and this goes on like this with B3, which you will use the next set of coefficients. So let's call it etc. Okay, now what about the next row? Now in the next row, okay, we will have a set of coefficients. Let's call them C1, C2, and C3. Okay, and in this case, what we will do is we will use the previous two rows in the same manner. So we will consider B1 with A3. So we will have C1 equals to B1 A3 minus A1 B2 minus A1 B2 divided by B1, and C2 will be given by B1 A5 minus A1 B3 over B1. Okay. So until we have, let's say, E1 here as a single and F1 as the last coefficient. So you will see that this is going to look like an upper triangular kind of matrix, because you will have zeros on the lower right corner of this array. Okay. Now, you know, this is a pretty old technique actually. If you're interested, you can take a look at Wikipedia with 1964 Routh-Hurwitz. Okay. All right. So what are we gonna do with this array? Is that we will actually investigate the first column of this array. Okay, there will be a set of numbers in the first column. And the last step, which is our step 4, is investigate the sign changes in the first column of the Routh array. Okay. So the number of sign changes, in fact, number of sign changes is what is actually what is important. Okay. The Routh-Hurwitz method states that essentially the number of sign changes in the first column is equal to the number of roots of Q of S equals 0 with positive real parts. Okay, so that's the main result. So a very interesting result, because essentially you construct an array of numbers from the given polynomial. You basically have a first column with a number of sign changes, and the number of sign changes tells you how many unstable poles you have. Okay, so this is also equal to number of unstable poles. If you don't have any sign changes, all the numbers having the same sign, that means you have a stable system. Let me show it to you with an example, okay? So here's our example. So characteristic equation is given, which is the denominator polynomial of the transfer function. Characteristic equation is given by Q of S is equal to S to the power 4 plus 3S cubed plus 2S squared plus S plus 1. Now you may, let's say in a question, you may need to actually obtain the transfer function and then the denominator polynomial to arrive at this point, okay? So this may actually come from, actually not may come, but comes from the closed loop transfer function. Okay, so in some questions you may actually need to derive the transfer function and find its denominator in order to obtain the characteristic equation. Okay. Now, but the problem here is that this is a fourth order polynomial. We cannot solve for the roots of this polynomial. We can only solve for the roots, for example, in MATLAB or a numerical analysis package. In MATLAB, we can use roots function to give the polynomial to get all the roots, okay? But what we want to do is use the Routh-Hurwitz method to find out whether this system is stable or not, okay? Is the system stable? How many, if it's not stable, how many unstable poles? Okay, these are the questions that we might be trying to answer. Okay, so let's construct the Routh array. Okay, we have a fourth order polynomial, so S4, S3, S1, S0. So the first two rows, sorry, I've skipped one of the coefficients, which is a deadly mistake. Okay, S2, S1, and S0. Okay, so let's the coefficients, when you are projecting coefficients from here to the Routh array, be careful, because if you have, for example, a missing coefficient, you know that the system is unstable, but you still want to maybe know how many poles are unstable, and in order to construct a proper Routh array, you need to also consider any zeros in between, okay? So here, my first coefficient is 1, my second coefficient, s to the power 3, is 3, my third coefficient is 2, my fourth coefficient is 1, my fifth coefficient is 1, and my sixth coefficient does not exist, so we put 0 instead. Okay, so let's construct the first layer of coefficients. Okay, so over here, what I will have is 3 times 2 minus 1 times 1 divided by 3. So this is going to be 6 minus 1, 5, so it's going to be 5 over 3. Okay, so this is the coefficient over here. What about the second coefficient? Over here, it's going to be 3 times 1 minus 1 times 0 divided by 3. So this is 0, and 3 cancel out, so you get 1 instead. Okay, so you have 1. All the rest of the coefficients turn out to be 0 because you don't have anything here. Okay. Now, what about the second row? Let's again change color as we did before. Okay, so here I will have 5 over 3 times 1 minus 3 times 1 divided by 5 over 3. Okay, so that's going to be 5 over 3 minus 9. So 5 over 3 over minus 9 over 3 divided by 5 over 3. So that's going to be 5 minus 9. It's going to be minus 4 over 3 over 5 over 3. So that's going to be minus 4 over 5. 4 over 5. Okay, so this is minus 4 over 5 in here. The rest will be 0. And over here, it's going to be minus 4 over 5 times 1, minus 5 over 3. So let me also do this for completeness. Okay, so it's going to be minus 4 over 5. Minus 4 over 5 times 1 minus 5 over 3 times 0. Whenever you have a 0 here on this corner, because of the later division by minus 4 over 5, basically what you get is this entry over here, right? So so this is 0, these cancel out, so this is equal to 1. So we have 1 over here. Okay, so let's consider the first column. So plus, right, this is plus, 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 minus, plus. Okay, so one sign change here, another sign change here. Okay, so we have plus, 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 minus, plus, two sign changes, one plus to minus and one minus to plus. Okay, so what we conclude using Routh-Hurwitz method is that we have two sign changes. Okay, so that means two roots of Q of S equals 0 on the right half plane, and that means system is unstable. Okay, so it not only tells us whether or not the system is stable or not, but it can also tell us how many unstable poles there are. Okay. Now let me try to solve another example and finish this video, which is approximately how many minutes now? It's 23 minutes, so half an hour is, I guess, a reasonable duration for a video. So let's have another example. So we have Q of S is equal to S to the power 5 plus S to the power 4 plus 2S cubed plus S squared plus S plus 1. So, okay, so let's leave this for the next video. So please try to, before moving on to the next video, okay, try to construct. First of all, take a look at this. Is there any missing coefficient? So it's a fifth order polynomial, 5, 4, 3, 2, 1, and 0. So all coefficients exist. Is there any sign changes? No sign changes, so the necessary conditions are satisfied. Okay, but we still don't know what's going to come out. Okay, necessary conditions are satisfied. Okay, so let us try to construct the route array and essentially talk about the stability and how many unstable poles in this for this characteristic equation. Okay, so we will continue on the next video trying to solve